Welcome to the TRAPPIST-1's solar system, a breathtaking collection of 7 Earth-like planets orbiting a red dwarf star. Discovered by the TRAPPIST telescope at Silla Observatory, this unique system is a cosmic anomaly with the most planets ever found in the habitable zone. Each planet could hold clues to life beyond Earth. What mysteries do these worlds conceal? Dive in with us as we delve into TRAPPIST-1's secrets and inch closer to unraveling the universe's greatest mysteries. Join our journey to know more about this discovery and if these planets could support life. Imagine venturing into a system where 7 worlds circle a single star, each one a unique canvas for potential life. The TRAPPIST-1 system, discovered by the TRAPPIST telescope, presents us with a scenario straight out of a cosmic tale. Each of these 7 planets orbits close to their host star, a red dwarf, a type known for its longevity and frequent flares. The key to life as we know it is water. But how can we tell if these distant planets have any? Through the transit method, astronomers detect slight dimming as planets pass in front of their star. This tells us their size and, with the star's characteristics, gives clues about their composition. 4 of these planets reside in what we call the habitable zone, a sweet spot, where conditions might just be right for liquid water to exist, given a thick enough atmosphere to ward off the star's harsh radiation. But let's dive deeper. What does habitability really mean in such a peculiar system? These planets are likely tidally locked, meaning one side always faces the star, basking in perpetual daylight, while the other side languishes in endless night. This creates extreme temperature gradients. On Earth, water and air currents distribute heat, moderating our climate. Could something similar happen on these planets? Scientists use advanced computer models to simulate these worlds' atmospheres and potential weather systems, searching for any sign that life-sustaining conditions could exist. Yet the presence of water is just the start. We also need a stable atmosphere. The atmospheres of these planets are subject to intense scrutiny as they hold the key to surface conditions. Through spectroscopy, using light filtered through a planet's atmosphere during transits, scientists identify the fingerprints of gases, each potentially a clue to processes occurring on the planet's surface or within. Red dwarfs like TRAPPIST-1 are both a blessing and a curse. Their longevity exceeds that of stars like our Sun, offering a longer timeline for life to potentially develop and evolve. However, their temperaments pose significant challenges. These stars frequently unleash stellar flares that can emit as much energy in minutes as our Sun does in a day. For planets orbiting so close, like those in the TRAPPIST-1 system, such flares are a serious hazard. Why are these flares so critical? They have the power to strip away atmospheres, particularly for planets without magnetic fields strong enough to deflect charged particles. Each flare is like a celestial storm, bombarding these worlds with high-energy radiation, which can break down atmospheric molecules and erode the very air needed to support life. Moreover, the proximity of these planets to their star raises another issue: tidal locking. This phenomenon means that each planet's rotation synchronizes with its orbit, always showing the same face to the star. Consequently, one side of the planet experiences perpetual daylight, hot and bathed in radiation, while the other side is cloaked in eternal darkness and cold. This extreme contrast creates harsh conditions for life as we know it, which typically thrives in more temperate and variable environments. Conversely, the outer planets, specifically T1, E, F, G, and H, show potential for retaining some of their water, making them particularly intriguing subjects for further study due to their placement within the habitable zone. The team's simulations reveal we find the interior planets T1, B, C, and D are likely desiccated for all but the largest initial water contents, larger than 60, 50, and 32, respectively, and are at the greatest risk of complete atmospheric loss due to their proximity to the host star. Despite the bleak outlook for these inner planets, there's a silver lining for T1C, which could retain significant atmospheric oxygen, a potential indicator of biological processes. As we continue to gaze at the stars, tools like the James Webb Space Telescope JWST offer unprecedented opportunities to peer into the atmospheres of planets billions of miles away. Scheduled to observe the TRAPPIST-1 planets, JWST can analyze the light passing through their atmospheres during transits, breaking it into spectra that reveal the composition of those atmospheres. This could show us signs of water vapor, carbon dioxide, methane, and even oxygen molecules associated with biological processes on Earth. The significance of JWST in future telescopes lies not just in their ability to detect these molecules, but in their ability to help us understand the dynamic processes at play. Each spectrum can tell a story of interactions between stellar radiation and planetary atmospheres, of geological and possibly biological processes that could be happening on these distant worlds. Future telescopes, like the European Extremely Large Telescope ELT and the Giant Magellan Telescope, promise even greater insights. These ground-based observatories will complement space-based telescopes by providing different types of observations that can help clarify the picture painted by JWST. For example, they can offer more detailed observations of the star itself, helping astronomers better understand the stellar environment that these planets inhabit. With these tools, the scientific community stands on the brink of potentially answering one of humanity's most profound questions: are we alone in the universe? Each observation, each piece of data brings us closer to understanding not just the TRAPPIST-1 planets, but also the broader cosmic contexts in which life might emerge. The TRAPPIST-1 system continues to be a high-priority target for observations, which are crucial to understanding the potential for life on these distant worlds. Thank you for joining us on this stellar journey through the TRAPPIST-1 solar system. As we ventured together beyond the bounds of our own planet, we uncovered the fascinating potential of these 7 distant worlds. Each discovery we discussed today brings us one step closer to answering the age-old question, are we alone in the universe? We appreciate your curiosity and your eagerness to explore the cosmos with us. If you found this exploration as thrilling as we did, don't forget to like, share, and subscribe for more insights into the mysteries of space. Keep looking up, keep wondering, and until next time, keep reaching for the stars.